Okay, welcome to Lecture 2. Again, we're talking about predicting physical properties, and this will be on what are called intermolecular forces, which depend strongly on the nature of the bonds, whether they're polar bonds or non-polar bonds. And so go ahead and copy down these definitions. You can pause the screen, and then we'll discuss. When we talk about intermolecular forces, we're talking about two different molecules and how they interact. And that's going to be strongly dependent on the types of bonds in each molecules, how strongly they can interact with each other, how strongly they can attract one another. The first kind of force is called a dispersion force. We can also refer to these forces as van der Waals forces. And sometimes you might see these on a website or in a textbook abbreviated, whether they're talking about dispersion forces or van der Waals forces, they're talking about the same forces. So sometimes they're just abbreviated VDW forces. You might see that. This is the weakest force. It's just a temporary attractive force. It's probably the hardest one to understand in terms of where it's coming from. We don't need to understand it. We just need to know that all molecules have these weak forces and that they're the weakest type of force. Essentially what they come from is the electrons are moving around all over the place, really. They're not confined to the bonds that they're in narrow little lines. They can actually move around quite a bit, and as they move around it causes very small positive and negative charges to develop, but it's temporary. And so these temporary charges that are weak in nature will actually attract or repel other molecules, but since they're temporary, they're very weak. And so this is the weakest force. The next one are dipole forces. And when we use the term dipole, we're basically talking about a polar bond. So essentially you could call this polar bond forces. These are moderately strong, and they're due to a permanent polar bond, which we've already discussed. In contrast, the van der Waals are the weakest force, and it's a temporary one. And so a good example of a dipole force is this molecule acetone. And you should be able to fill in the polar bonds and the charges on acetone. We used it as an example. But we know the oxygen is partially negative and the carbon is partially positive. And I'll put this in a different color. And so a single molecule of acetone won't have, there's nothing you can do with it. But molecules are always around other molecules, especially in the liquid or solid state where they're closely interacting with many different molecules. And so if we envision an interaction between another acetone molecule, these molecules will line up in a complementary fashion where the opposite charges are nearby each other. So for example, in this molecule of acetone that's kind of turned upside down on its head, the negative oxygen will be down here, and the positive carbon, or the partially positive carbon, will be up here. And these, of course, can be in three-dimensional space, but this allows the negative charge, which just like a magnet, the negative end is attracted to the positive end. Well, these charges attract, and it's a fairly strong interaction because this is permanently negative and that's permanently positive. Likewise up here, these two ends attract. And so that attraction, the way it will line up to put itself in the best position, allows these two to stick together with some strength. And so they're interacting based on the nature of those charges. if a molecule of acetone lined up with this one, the same way, then you would have more, as it approached, it would have more of a repulsive interaction. As the two positive ends would be near each other, that would start to repel as they got close. And if the two negative ends were near each other, that would also repel. And so what would happen is it would flip around and become attracted. Just like if you've ever played around with two magnets, if you try and get the repelling ends together, one of them will flip and they'll stick together. Similar to polar molecules. The third intermolecular interaction, and the final one that we'll discuss, and the strongest one, is called hydrogen bonding. And it's essentially a special form of a dipole-dipole interaction that's more powerful. So a molecule capable of hydrogen bonding will be one that contains either an OH or an NH bond. And so, as the name implies, it definitely must involve hydrogen. And with an OH or an NH bond, because there's such a large electronegativity difference between the two, these are highly polar bonds. And what can happen in a hydrogen bond is best illustrated with something simple like water. If we have water, well, two molecules of water can interact through hydrogen bonding, and it's specifically oxygen and nitrogen because these molecules always have lone pairs of electrons. And so the electrons themselves, we know, are negatively charged. And so if we also know that this hydrogen here is partially positive and the oxygen is partially negative, well, then this partially negative electron over here, or partially negative oxygen over here, can actually use its electrons to form what's called a hydrogen bond. And so I'm just drawing a dashed line. So basically these electrons, they don't form a normal bond, what we call a covalent bond. Those are much stronger. But they'll form what begins to look like a covalent bond. And so the electrons start to interact with that hydrogen, and it's stronger than a dipole-dipole interaction. And so this would be one example of a hydrogen bond. And so in a glass of water, there's trillions upon trillions of water molecules, and most of them are hydrogen bonded to many other water molecules. So for example, down here, we could have an oxygen of a different water molecule, and it could be hydrogen bonding to that hydrogen. So these are two examples of hydrogen bonds. Now water's a pretty simple one. But we can look at a little bit more complicated example. And I've abbreviated this structure a little bit to show. In this molecule, which is our secondary amide, we know that we have a negative oxygen in the carbonyl group, and we have an NH bond here that is capable of hydrogen bonding. And so this molecule, if you envision many of these molecules around, they'll line up such that however a hydrogen bond can be formed will be a preferential way for the molecules to organize themselves. And so the oxygen of one molecule can line up to be very close to the hydrogen of the other molecule that's capable of hydrogen bonding, the nitrogen hydrogen. And we can see a very strong hydrogen bond between the two molecules, as the electrons from this oxygen are attracted to this hydrogen. Now it's possible that the nitrogen could also hydrogen bond in this situation, but that's actually not the most possible one. But you're not responsible for predicting which one will be stronger. You would just have to know about their nature and perhaps how to label them if the structure was drawn out for you. Also, for example, it doesn't have to be between molecules that are the same. If this molecule is dissolved in water, and there's water molecules around, well, you might have a water molecule nearby. That water molecule can then hydrogen bond with the carbonyl of this amide. And so now we have hydrogen bonds between two different molecules entirely, a water molecule and this amide molecule. Alternatively, we could also have a water molecule down here, hydrogen bonding with this nitrogen hydrogen. For hydrogen bonding, you'll always have a hydrogen bond donor and a hydrogen bond acceptor. The way this is drawn here, this water molecule would be the hydrogen bond donor because it's donating its hydrogen, or its hydrogen is involved in the hydrogen bond. And so this would be the hydrogen bond donation, or the donating bond. This oxygen of this molecule would be the hydrogen bond acceptor. And so we're specifically talking about this atom here. In terms of the donor, we can refer to the entire oxygen-hydrogen set of atoms. And so both of these atoms are the donor, because it's based on that bond. Likewise, down here, this would be our hydrogen bond donor, because this is the hydrogen that's involved in the hydrogen bond. And this would be our hydrogen bond acceptor. And so in hydrogen bonds, the hydrogen bond acceptor is always an atom with lone pairs. And I can put that here as well. so this will be an oxygen or a nitrogen most commonly. However, it could also be fluorine or chlorine, as those are also very electronegative elements. But these are by far the most important, oxygen and nitrogen as hydrogen bond acceptors. So down here we have another hydrogen bond donor, and oxygen of water would be the hydrogen bond acceptor. Okay, now we want to get to the most important part of all this. How do these forces, or how do these properties, how do these forces affect the physical properties? Because we want to learn something from a structure and be able to predict things about their physical properties. And so I have some data that we'll look at and then we'll analyze. And so we want to look at how these forces affect melting point, boiling point, and water solubility. So here are three different molecules. Notice they all obey the octet rule. And we got a lot of hydrogens drawn in here. So here's our data. Now, importantly, you do not have to memorize any of these numbers. What you'll be expected to do is to look at this kind of data and rationalize the trends, and we'll go through it in some time. First of all, let's think about the functional groups for these molecules. You'll have to think about functional groups all the time. This is just an alkane. It's contained completely of carbons and hydrogens, and they're all single bonds, so it's an alkane. This one here you should be able to label. This is an aldehyde. It's got that carbonyl, and it's where one of the atoms bonded to the carbonyl carbon is a hydrogen. That's our pattern for an aldehyde. Over here we've got an alcohol. And this is actually a primary alcohol because the carbon bonded to the OH group is only bonded to one other carbon. Well, okay, those are our functional groups. If we look first at the boiling point data, we can see that it's increasing from left to right. Well, what does that mean? Well, in order to get something to boil, that means we're going from the liquid phase to the gas phase. And so it takes energy to do that. We know that because in order to get water to boil, to make our macaroni and cheese, we've got to heat it up on the stovetop or in the microwave for a long time. And all that's doing is putting energy into the liquid. When it boils, we've given it enough energy on average to allow for molecules to consistently go from the liquid phase to the gas phase. And when you stop supplying that energy, it stops boiling. The reason it needs energy to boil is because you have to break all of the interactions of a single molecule because it's in a liquid phase and then it goes to a gas phase. So if the interactions between the molecules are weak, then it's much easier to break them. And so we can boil that liquid at a much lower temperature. So for pentane, this molecule, the boiling point is really low. Notice all of these are about the same size. And so it doesn't take much energy to boil pentane. What do we notice about the bonds in pentane? Well, they're all non-polar bonds. What types of forces does this molecule have? Well, it only has dispersion or van der Waals type forces because there's no polar bonds. If we look at the aldehyde, well, here it's got a polar bond in the carbon-oxygen bond, and then the rest of it are all non-polar bonds. But that one polar bond makes a big difference. Notice we've gone up in boiling point by 40 degrees. That's a huge jump. That's a lot more energy to boil this solution. And so this molecule, as a whole, we would say has both the dispersion or van der Waals forces, and it also has dipole-dipole forces. So those dipole-dipole forces are much stronger than van der Waals or dispersion forces. And so they allow these molecules to stick together more strongly. So it's harder when you boil a solution to provide enough energy to pluck just one of them out of there at a time and break all those interactions. If we go to the alcohol, well, here we've got van der Waals or dispersion forces because all molecules have them. And then we've got some polar bonds, carbon-oxygen and the oxygen-hydrogen bond. So it's definitely got dipole-dipole. And then it's also got an OH bond, so it has hydrogen bonding as well. So that's the strongest force. And so notice it's gone up 42 degrees Celsius. And so this takes a lot of energy to boil compared to the others. And that's because it has these hydrogen bonds in addition to the others that are take a lot of energy to break. We see the same trend reflected in melting points. Now the melting points are negative, so it's somewhat counterintuitive. But essentially, pentane will melt from a solid into a liquid, which requires the same kind of breaking of interactions at negative 130 degrees. And so that's very, very low energy. There's not much energy around at negative 130. It's very cold. But even at that temperature, this will melt into a liquid because it takes very little energy to break the interactions in the solid state. Then, nice and warm and toasty at negative 96 degrees Celsius, but a significant jump in energy from the previous one we see the same thing. So basically, the melting point trend reflects what we observe in boiling point. The last thing that's directly related to these intermolecular forces is water solubility. We tend to think about water solubility because that's, especially in this class, that's probably the most important solvent for us. But so for water, what we see in the data is that as you get more polar bonds, and especially the capability to hydrogen bond, you get to be more soluble in water. And so we don't need to worry about these units so much, but basically the larger the number, and this is a decimal value, the larger the number, the more of it will dissolve in water. So this is barely anything, 0.04 grams for a liter of water. And so that's a tiny, tiny amount that can dissolve in water. Basically, water doesn't like it. It won't let it dissolve very much. When we have a polar bond, water likes it a lot more and will allow it to dissolve in. So we've got a huge jump from the nonpolar molecule. Then if you throw in a capability to hydrogen bond, the water solubility goes way up again, about 10 times the amount. So this is actually really pretty soluble in water because of that hydrogen bonding capability. And so we've gone through these trends, and now we want to physically write them out and give some rationales to go over it. And then we'll look at a couple examples that you'll do. And so these are trends, and I know I discussed these previously, but I wanted to write them down so you could have them in a nice condensed form. These were the trends we observed in that data, and these are trends we'll see in all sorts of molecules where comparisons can be made. So now I want to give the rationale for these trends. water solubility. You may have heard the common expression that's not very, it's very simplified, but the common expression that like dissolves like. Well, it applies right here. Water dissolves things that are similar in structure or physical properties to itself. And that's what we mean by like dissolves like. And so water will preferentially dissolve things that have polar bonds, especially if these are bonds that can hydrogen bond. So molecules that hydrogen bond are the most likely to dissolve in water. But also very polar molecules, even if they can't hydrogen bond, can also dissolve in water quite easily. Water does not dissolve molecules that have a lot of nonpolar bonds. And so the nonpolar bonds and nonpolar regions of a molecule are very much unfriendly regions for water. And so we'll examine this trend in a data set later. So it comes down to the ratio of polar bonds to nonpolar bonds. And there's not a magic number here, but basically for every polar bond you have, you can only have so many nonpolar bonds, and then your water solubility starts to go way down. So this is one rationale, thinking about water.